Okay. Okay, so I hope the people on Zoom now hear me. Good. So quantum communication, is a study on its own. It's just somehow instead of communicating via classical means, we now use quantum channels. Yeah. So for example, I take a quantum device, encodes information, and I send it to you, or I give it to you to your lab, and then you try to decode. Okay. But there is also this way of seeing quantum communication as the dual side of the coin to what I started out talking about, namely having a quantum device that performs some quantum computation that we wanted to perform. For example, factor a large number. And then the noise that is induced by the environment necessarily somehow tries to decohere the system and mess with the computation. And so we need a way to protect the information from this. Okay. And if we model the environmental noise in the same way that we model the communication link in the information theoretic picture, then the two things are really two sides of the same coin. Okay? And information theory is a mathematical framework for communication. So there, this limit of how much information can be processed so that it remains faithful and decodable, or the amount of information that can be transmitted through a channel, so such that the decoder can decode this faithfully. Both of these limits are expressed by this so-called quantum capacity of the channel. Okay. I will not define this in the information theoretic way for you because this is a very technical definition, and I don't think you will take away a lot. If you're interested, I'm very happy to talk about this in more detail. Right now, just think of this in this like slightly hand-wavy way of the quantum capacity marks the optimal rate of faithful quantum communication through a channel, or equivalently, the optimal rate of faithfully processing quantum information in a quantum device. Yeah. And in information theory, once you define a communication task and then a certain capacity that somehow characterizes how well can you perform this task, then we also want to find a formula to actually compute this thing. Okay, so having this operation definition is one thing, but writing down a channel, then asking, okay, what is that limit for this channel is the other thing. Yeah, and so these are the so-called coding theorems in information theory. And for the quantum capacity, there was a long series of work in the late 90s and early 2000s that culminated in this so-called quantum capacity theorem. And it tells us that the quantum capacity is given as an optimization problem over an entropic quantity that is called the channel coherent information. Which let's try to unpack this maybe a little bit. So we have our channel from A to B. And then we know from the theory of open system dynamics that you can always write a channel between two quantum systems as an isometric evolution on a larger system. Yeah, and in this way, you kind of return to the Schrödinger formulation of quantum mechanics. Yeah, so what that means is that A and B are the two input and output systems of your channel, and then you can assume that there's some environment E, and if I bring in this environment, then the evolution on the whole tripartite system is isometric, so kind of reversible. And the noise comes from not having access to the environment and somehow tracing it out. Okay, so the channel here is then given by applying this isometry and then tracing out the environment. But information theoretically, this is actually a very nice way for us to also understand what we lose. Yeah. So here, somehow the noise that we model can also be understood as some information going to the environment. Yeah. And this is a so-called complementary channel from A to E, where instead of tracing out the environment, I trace out the receiver. Yeah. So for the complementary channel, the environment is the actual receiver, and Bob is the environment. Yeah. So we kind of flip the roles.
Do you remember? Came up with the letter E for eavesdropper or environment. System G is a move, right? E for eavesdropper and environment at the same time.
It's kind of nice that it works for both physics and cryptography somehow. Yeah, I mean, like some people just call it C, but then
but E is much better. You have to.
Yeah. So if A and B are Alice and Bob, then E is sometimes Eve.
Sometimes eavesdropper.
Yeah. Anyways, I do not know who came up with this first. Okay, and so now we have two channels. Okay, we have the channel itself, and we have this complementary channel that somehow models how much we lose to the environment. And now the coherent information, or at least one part of this formula, tries to measure how much more information we can get to the receiver versus the environment. Okay, so we choose some input state rho. This is an input state to the channel. And then we measure how much entropy, S is a phenomenon entropy, how much entropy goes to the receiver versus how much goes to the environment. So we measure the information in using phenomenon entropy. And here we look at the information gain that Bob has over the environment. There's also, you can also look at the so-called purified picture where instead of sending information to Eve, you ask how much information is preserved when I send half of a state through the channel. Yeah? So you have some entanglement with a reference system, the channel introduces some noise, then you ask how much entanglement is left, basically. Yeah? I will come back to that picture next slide, because that is a useful way to think about this. Okay, so these two things are equivalent. And now the annoying thing is that this quantity itself doesn't yet tell us how much information we can transmit. So here we have this so-called regularization where we ask not just for like a single channel copy, how much information can Bob get over Eve, but we actually do this on large multipartite systems, and the channel acts on each system in the same way. Yeah, so this tensor product here is the so-called IID scenario, or independent and identically distributed noise. This is a huge assumption that is not really justified in most experimental applications, but in information theory, this is it's still a hard problem even if we make this assumption. Okay. And now the quantum capacity theorem tells us that the largest amount of information we can transmit is actually the supremum over all of these channel coherent informations, where we do this for larger and larger systems. And we will see in a second that unfortunately this is actually necessary to write it like that. But there's a question.
So it's really easy to understand from the picture. I think about leaking information to the environment, some of it going away. But of course, you originally introduced this as noise from the environment, which is something else coming into my detector, some other random thing coming in. So it's just a little harder to see in this picture how that error goes from the environment into B.
Yeah, the way to think of it is, at least for me, is that when you do a quantum computation on a device, then your device gets entangled with the environment in the process. And so therefore, this will hurt your computation. And so then establishing the entanglement with the environment is basically taking, like, this acts on part of the system that has some correlation with the rest, but now the environment gets it. Is the way to think about this.
I feel like that involves taking something in from the channel from A, going to A to B and dumping into the environment, as opposed to going the other way, having something from the environment going into the channel. It's just some extra noise. It's not necessarily helping an eavesdropper, it's just some random stuff.
I'm not fully sure I understand the...
Included, but I don't quite, it's hard for me to see how.
So the way you can think of this is that your quantum device. So first of all, if you're in the error correction picture, then A and B are somehow the same thing, and the noise acts on your device. Yeah. So somehow the physical separation between Alice and Bob as two people or two parties, that's more the communication framework, right? In a quantum computation, A and B would somehow be the same device, and this is like a time step, right? But the way this works now is that your quantum circuit is just part of a larger system. The whole thing is a unitary evolution, but you cannot control how much of that unitary evolution actually acts between your system and the environment. And so, yeah, like me saying that the environment injects noise in the system, I don't know, you can probably also make sense of that mathematically, but that's more like a figure of speech in a sense. But like what I really mean is this, that you can typically not avoid that your system develops correlations with the environment. And then if you do not have that environment, then the effective evolution of your system will appear noisy. And then, yeah, this is the way to model it. Okay. Okay. So in information theory, whenever you have this, it's bad news. Okay. So because if we really need this, then what does this mean? This means that this is an unbounded optimization problem because no one tells me a bound on the end that I need to go to. Yeah, and in fact, there are constructions of channels for which that you can push this out arbitrarily far. Yeah. And that's bad because that means we basically cannot compute things. Yeah. And the reason why we have this regularization is this so-called superadditivity effect that is at play here. So here I want to think about query information in this in the purified picture. Okay, so Alice and Bob are the two people who try to communicate, and you can think of the query information formula as Alice prepares some entangled state in her lab locally. Yeah. R stays with her the whole time. A is the input to the channel, so A is somehow what she tries to send to Bob. Because of the channel noise, this will now be, if she starts with a pure state, this will in general be a mixed state, which reflects the fact that you have noise. And then you ask how much of the correlation that Alice started with is left. Yeah, so this is this kind of like data processing point of view. Okay, and then the query information really measures how much information or how much correlation is left using this entropic formula, S of B minus S of E. Yeah? Entropy of, in this case, S of E, the environment is actually the same as just the joint entropy in this bipartite state. Yeah. Yes.
Just to clarify, in this picture, if we apply some sort of correction to the error, we should be getting back the maximal entanglement.
Ideally. Typically, that will not happen, but if you have a perfect error correction code, then yes, you do get all of that back. Yeah. But there's the noise has to play along somehow. Like it can't be too much and certain. Right. So ideally, you would somehow like be able to undo this noise. Generally, you cannot do this, and then your information goes down. Yeah. So this is this so-called data processing principle that whenever you have noise, this can maybe stay the same. It usually goes down. It can never go up. You never gain more information by a noisy evolution of your system. Okay, but now imagine that instead of preparing this bipartite state, Alice actually prepares a multipartite state. Yeah, so here now she again has some reference system. You could take as many R's as you have A's here, but that doesn't really matter too much. The important part is that you have multiple channel input systems here, yeah, multiple A systems. And there's now some more complicated entanglement structure in this multipartite state. Yeah, so this is not just pure bipartite entanglement. This is some graph state, a GG state. Yeah, we'll come back to that, what that should be. All of these A systems now undergo the evolution. So they are sent through the channel in the communication picture. And then you do the same thing. You ask how much entropy reaches Bob versus how much entropy is in the joint system, which again measures this information gain that Bob experiences. Yeah.
In the picture, it seems like R is being tangled with the R B, so it's actually with all three B's.
Yeah, that was just it was hard to visualize this and not be too confusing. Like, don't take these lines seriously. It's just like a representation spot. Okay, so here we do the same thing. We ask how much entropy is in B versus how much entropy is in RB. Because we're using here in this particular example 3 input systems, we do need to normalize this. Otherwise, we would be comparing apples with oranges. So we talk about how much information gain is there per channel copy that we use. Yeah, so this is in information theory. This is kind of like averaging out the fact that you have like a larger system now, and you can in principle transmit more. But now, if you look at this quantity here, it could happen that this is actually strictly larger than this. And indeed, that does happen sometimes. Yeah, so the idea to think about this, how to think about this is, again, we have some more interesting multipartite entanglement structure in the input state that somehow mitigates the noise in a useful way so that that coherent information is actually larger than if I do this with a single channel copy. Yeah, so you can think of this in the error correction sense if you want to. And in fact, a lot of states that demonstrate that do come from error correcting codes and try to make use of this. So there's also a mathematical link between the two ways of seeing this. Okay, and so this is not just something that is predicted by information theory. This is, we actually see this. Okay, so there are some very well-known channels for which this was realized a long time ago. Yeah, so this also was part of this early work by the information theorists on this in the late 90s. So a lot of channels that we actually also care about from an error correction point of view somehow exhibit the superadditivity effect, where you really need to go to these multipartite states in order to maximize this quantity. The most well-known one is probably the depolarizing channel, which applies with equal probability one of the three Pauli errors to your system. You can then generalize this model to having different probabilities for the different error operators, X, Y, Z. We will talk about some special examples of this later. And then a lot of my recent work, also during my postdoc years, was trying to understand this phenomenon better. And one way of doing this is trying to write down channels that are simple and still do it, so that we can say something analytical about it, maybe get a sense on what the magnitude of these things are. And with people in Colorado and IQC, we came up with this construction of a so-called defrasure channel, which is dephasing noise followed by erasure noise. Yeah, so both of those are by themselves very well understood channels from the point of view of quantum information transmission. But when you put them together, suddenly they do weird things. Yeah, so they have these superadditivity effects, etc., etc. There's also a version of the amplitude damping noise that has a temperature, and so this is called generalized amplitude damping channel, for which we also don't know what that quantum capacity is, and you can then study again this effect here. Yeah.
So is this quantity always bounded by some finite number of particles, or is it the case that it could just be monotonic out to the
Yes. The maximal amount that you can transmit is the minimum of the log of the dimensions. And so by data processing, it can never be more larger than that. So that would be an identity channel that kind of like gives you a qubit.
Then I need a multipartite state in order to maximize this quantity. Here you have three of them.
Yeah, so I normalize. I normalize here. So on average, I can never exceed what an identity channel would do, because identity channels are actually additive, so that those numbers will always be the same when you maximize. So you have a natural upper limit, yeah, and you have a natural lower limit given by 0, because the quantum capacity is an operational quantity that is just never negative. Okay, and so we're interested when we have a channel in front of us that maybe models the noise in our device, then we want to ask, does this effect exist for this channel? Because if yes, then that is the actual limit, and those are the actual weights that I could in principle use for communicating information or protecting information at that rate. So if we don't harness this effect and don't understand it, then we will not go to the actual limit that we have in the system. From a communication point of view, this is very natural, especially if you have a lot of noise, where this quantity here might actually be 0, whereas this is still non-zero. And so this is a somehow extreme effect of this. Okay, but the problem of this is really that this superadditivity, it really requires this regularization here, this supremum over all numbers of channel copies that we actually have to check here. And so it's a lot to ask to actually compute this, unless your channel has nice properties. But somehow generically, channels don't have these nice properties. And so what we do when we can't compute a quantity is we try to find bounds and try to sandwich it as much as possible. I've also done a lot of work on upper bounding for quantum channel capacities. Here, the idea is usually that you try to relax your problem so that this limit or regularization goes away. So for example, you can think of, instead of using the LOCC framework for the experts, I use something that preserves public partial transpose. there's different ways of doing this, but the idea is always that your communication setup of transmitting core information, if you make it a little easier, it becomes mathematically tractable. And for us, this always or usually means that this limit here goes away. Okay. And one possible way is to use the transpose map actually to get an upper bound on this corner capacity. And so this is a function that in finite dimensions you can just efficiently compute, and it gives you an upper bound that sometimes is actually quite good. Sometimes it's not good. You know, the problem with these is always that you have to tailor this to the channel. But in our talk, we will be concerned with lower bounds. Yeah. And so here, just mathematically, the way you approach the lower bound problem is to realize that this quantum capacity theorem, it's actually two optimization problems. Yeah, you have an outer and an inner optimization. The outer optimization is optimizing over these number of channel copies, so like the number of input systems that you check. And then in the inner optimization problem, you just try to find now a nice state on that number of systems that hopefully, whose entanglement will hopefully somehow mitigate the noise a little bit and make the query information positive. Yeah. And so therefore, when you try to determine lower bounds on the quantum capacity, you do exactly that. You have some computational method that allows you to go to a certain number of channel copies. I will, in a second, this is obviously related to the fact that we can't do this efficiently for large systems. You fix some n, and then you try to maximize over some ansatz that you have that you think will be useful for the channel. And then hopefully you will get some positive query information value, which always is a lower bound to the capacity. Yeah. And again, we will especially be interested in this very noisy regime where anything positive is good, is a result somehow, because the channel is already so noisy that most input states do not actually give you a positive contribution. But this is related to the hardness of this problem is related to the dimensionality curse in quantum mechanics. Okay, so we know that multiparted systems are modeled by the tensor product of state spaces, and so you have exponential scaling in your system dimension. And so even for qubit channels, if you don't have a clever ansatz, then solving this optimization problem you can do for n equals 5, 6, 7, something like that. But then it stops, basically. And so that is a problem, because that makes us actually not understand these quantum capacity quantities, or more generally channel capacities, because these optimization problems are hard and their scaling is horrible. And they're also, it's not just that the scaling is bad, but they're also lacking nice things like convexity. So from an optimization point of view, those are also just hard problems where you're not guaranteed to find a global maximum, et cetera, et cetera. So somehow bad news all around. Unless you can somehow, at least with this problem here, try to deal with the complexity by reducing it. So one way of doing this in mathematical physics is using symmetries. So symmetry is the principle, you do something and nothing happens. And so that eliminates degrees of freedom. Yeah. So a good example is this rotational symmetry in Euclidean space. If I give you some arbitrary 3D body and I don't tell you anything about it, you'll have a hard time like describing this mathematically. If I tell you that something is rotationally invariant in 3D space, then there's exactly 4 degrees of freedom left. The position of the radius of the sphere and the position of the center of the sphere and the radius. Yeah. So this is in a way a very extreme example of how symmetries reduce your complexity, where here I might need a lot of numbers. And if you think about like area filling curves or something like that, then this might be actually really bad. But 3D rotational symmetry simplifies it in a huge way. In confirmation, symmetries are a little more involved than just rotational symmetry in 3D space, but they're still tractable. And the two that are especially relevant in many parts of confirmation theory, but specifically in these communication problems, are these two symmetries that come from the symmetric group and the unitary group. And the idea is that we have these multiparted systems, yeah, let's say n qubits, and then I can permute my systems. Yeah, so the symmetric group has a natural action on this space by just permuting the tensor factors. And another quite natural symmetry is that I apply some basis transformation on each of the system. I could do this independently, but it is actually quite useful to think about just doing this in a coordinated fashion where I apply the same transformation on each system. Because if I do this in a coordinated fashion, then these two symmetries here, the one given by the unitary group acting so-called diagonally, because it's the same everywhere, and the symmetric group acting by permuting factors, those two symmetries actually commute now. Yeah, if you think about this, then it doesn't matter which one I do first. And you can say a little bit more about that, and I will tell you this duality in a little more detail in a second. And the fact that these two symmetries play nicely with each other has a lot of consequences in our conformation. Again, this is a very useful toolbox. But for us, it will actually be very useful in reducing the complexity of these optimization problems. And the way we do this is the following. So if you look at these results on super additivity of this query information, then basically the first example of a code that did this was one of the most basic error correcting codes that you can think of, namely the repetition code, where you just instead of sending a 0, you send 5 zeros, or instead of sending a 1, you send 5 ones. You can make this a little more general by giving different weights to the two code states. Yeah, so this can be useful. And so then this is what we call the weighted repetition code. It's the marginal of a GHZ state. Yeah, so that's the connection to physics. And we know from the literature that these types of codes typically, for example, for the depolarizing channel, they give us the super additivity effect. So these codes are often much better than single letter codes where you only do something on a bipartite system.
The repetition code is extremely fragile under Z error. But if you have a multiple single qubit, wouldn't that be larger code repetition?
Yeah, I will come back to that point. You can do like a short code type thing here, and that.
Is it some additional layer on top of repetition code or?
Okay, so I'm calling this repetition code because it is a repetition code, but I'm not looking at this as an error correcting code, in a sense. So I'm not studying this as to how it corrects a Z versus an X error. It's just, it turns out that mathematically it has still enough structure to give you something better for the query information. Yeah, but I will come back to that point of how you can improve this if I have time. Okay, and if I go back to these symmetries, then you realize that the code is actually invariant under this type of symmetry. Yeah, so it's this convex combination of so-called IID or tensor states. So if I permute my systems, nothing happens to the code.
Right, and that's why are you interested in this sort of thing in particular, this weighted repetition code?
Because it gives us
Better bounds for
better rates for information transmission.
better rates than what?
Then if compared to what you would get if you only solved this problem here. So kind of like the optimal thing, for example, for the depolarizing channel, here is just a bell pair, like an EPR state. That gives you a certain rate, but as the noise gets larger and larger, this becomes useless at some point, whereas when you do a repetition code here, then you will still get positive rates.
The next step would be these permute more than 1, 0, and 1.
Yeah, you could do that, but it turns out that this is not, like for the channels that we care about, it's not actually that good. But yeah. It is you can kind of ask what kind of symmetry do I want to impose. Like I will come back to that at the end of the talk. The main observation here for our paper is these codes are permutation variant, so nothing happens when I permute systems. And when I send them through the channel and the channel acts in the same way on each system, then naturally you preserve that permutation variance. Yeah, so the IID form of the channel here maps this to another permutation invariant state, which is a little more complicated now. But because of the permutation variance, the hope is that you can still describe this efficiently and then compute its entropes. And that's exactly what we're doing. The framework for this is representation theory. So let me give you a very brief, a very brief introduction. So representation theory is studying an abstract group on a concrete vector space, basically. Yeah. So you try to use linear algebra methods, very fancy linear algebra methods, but in the end, it's linear algebra methods to study an abstract group that operates on some vector space. So in mathematical language, we say that there's we have our group, and we have for every finite dimensional vector space, we have this group of invertible operators, the general linear group. And then a representation is now a group homomorphism, which means that whenever I do something in a group, it's the same as doing the same thing with the operators on the vector space. Sometimes I can restrict this to the unitary operators, and we will often do that because that's very useful for quantum information. And then when I have these representations, and the two that I showed you before, namely permuting systems in a tensor product and acting with the same unitary on each one, those are examples of representations. So those are representations of two different groups, the symmetric group and the unitary group, on the same representation space. So that's the important part. And once I have these representations, and sometimes they're somehow naturally defined for us, we can ask, what are the so-called building blocks of these representations? Yeah, so what are subspaces under which that stay invariant when I act with my group on these subspaces via the representation? And these building blocks or invariant subspaces, the smallest ones that we can find are the so-called irreducible representations. So those are somehow parts of the system on which the group acts and nothing, somehow I never leave that space. And then I cannot further decompose them. So those are really the building blocks. And then in representation theory, where we, in certain situations, and for us, this is always satisfied with the groups that we talk about, we can completely reduce a representation into these irreps. Yeah, so we can find some basis of the full representation space such that I can write it as a direct sum. So think of this as somehow orthogonal parts of your space, where I have each of these irreps appearing a number of times. Okay, and then usually the way I do this here is that I have some index that labels my irreps. So this is for the groups that we care about. It's known what labels these irreps and what they look like. And the groups that we talk about always have like a certain set of irreps. And so I can, when I decompose my space, I can kind of group them by whether they're isomorphic or not. Yeah, so I will typically find these irreps with a certain so-called multiplicity. And then this isotypical decomposition gives me a decomposition of the space into these irreps that I can now use to try to simplify my objects that I talk about. Okay. And the two groups that we care about, a little more precisely, the representations of the two groups that we care about on our n-qubit space that describes multipart entangled states, they have a nice feature called Schur-Weyl duality, where I told you before, if I think of these two actions of the groups, they commute. So I can apply either one first. But then it actually turns out that a little more is true. They don't just commute, but they generate all of the operators that commute with the other thing. So in mathematical language, it means that they generate each other's commutant on this space. Yeah, so that means that if I have something that is invariant under one group and its representation, I kind of know that it has a block structure with respect to the other group. And so this is what achieves this reduction in complexity. Yeah.
The previous slide you said that it's like the 0 and B are the irreducible, but I guess that's not.
No, I kind of like glanced over that a little bit. So we call something an irrep when the only invariant subspaces are the space itself and the triple one, because they are somehow always generically invariant. But if there is no non-trivial invariant space in there, then it's irreducible. It's a definition here, and then here it says that if I decompose my representation space with respect to these two representations, I can do this somehow individually. then the irreps of one group will be the multiplicity spaces of the other group. So they're somehow paired up. Yeah. So these two groups, they form a dual reductive pair. This is called representation theory. There are other examples of this, but the symmetric group and unitary group are so fundamental for us that this is the most useful of these duality results, at least for my research so far. Okay, I'm getting very close to time, and I'm just starting the actual results. So let me maybe try to do a little digest here. So let me make this point once more. The starting point for us is to observe that when I have a permutation invariant code, so a state, and this the repetition code from before was an example of this, okay? But I can now more generally say, let's fix some state that is invariant under permuting the systems. Then when I look at the output under some IID channel, then this remains true. And we actually, for technical reasons, we restrict to a certain subset of permutation invariant states, which are given by these convex combination of IID states. And current work is to generalize this to more interesting states. Okay, but the whole point is now that because of this duality, when I have these invariant states, then a result called Schur's Lemon representation theory basically tells us that invariant states have a very nice structure with respect to this decomposition into irreps. Yeah, because things that commute with an irrep basically have to be trivial, is kind of like the one-line explanation here. And so what this means for us is that I have this quantum state on an n-qubit system. So this is a d to the n times d to the n matrix. So a large object, generally. If I use the symmetries, then it's actually block diagonal in a very nice basis, where these blocks are attached to each irrep of the symmetric group. And I'm only like outside of these colored blocks here, I have zeros. So I actually have a lot of sparsity in the matrix now. And the nice thing is that the dimensions of these blocks, so somehow the density operators that are left after I symmetrize or after I use the symmetry, they're now small. A little more precisely, they're polynomial in n instead of exponential. Yeah, and so this is the starting point where, okay, if I can make this ansatz, it is a restriction, okay. The repetition code and the results about it tell us that it's not a bad restriction per se. So this is where the literature comes in. But it tells us that among this code family, I can actually efficiently evaluate these entropic quantities and then try to understand how large the quantum capacity is here. And there's also, since these groups and representations are so well studied, there's also explicit constructions of doing this, okay? So if you give me these row i's, then there is a way to actually construct these density operators and compute their entropies. So this is the technical part of our paper in a sense. Okay, and so then I can leverage this block decomposition of my output states. And then I get this formula for the information. I do not want you to parse this. This is a little nasty. What I want you to take away is that it is basically a sum over irreps of some functions of operators. And everything that you see is polynomial for the right channels, okay? So you kind of like a fix the channel, which means you fix the Ds, like the input and output and environment dimensions. But then we look at the n scaling. We look at more and more channel copies of this problem. And then this has polynomial scaling. So in principle, this gives us a way to try to compute this thing for n's that would never be accessible to us. So if you look at certain low rank states for qubit channels, then we can go all the way up to n equals 100, which is quite nice. So this is like the regime where tensor networks are also operating sometimes. And it is computing entropies. So this means that you have to compute eigenvalues of density operators, and you have these convex combinations here. So this is not straightforward, and a computational bottleneck. And the representation theoretic ansatz somehow deals with that. Yeah. to some extent. We did apply this to some channels that we care about. And we especially care about these so-called parameterized column channels, where we have some real parameter x, which we think of as a noise level. And then the larger the x, the more noise we have, and the smaller the column capacity is kind of the idea. Yeah? And so for the channels that we look at, when the x is 0, you have an ideal channel, no noise. And when the x is 1, you have like maximal noise, like somehow completely useless. It destroys any information you put in. And then, so you have, for these channels, the corner capacity is a non-increasing function in x that eventually becomes 0 and starts at 1 or log d, where d is your dimension of the system. And so now you ask, where does it cross, or where does it become 0 the first time? What is the called threshold? Yeah. Another piece of confusion, this is related to an error correction threshold, but it's not actually the same number for a given channel, because here you don't care about decoding and stuff like that. Yeah? So it is a little treacherous to use threshold, and we have gotten like questions from error correction people who kind of like think this is what they think. It is related, but not the same thing. And we then, let me maybe just highlight one channel, because I'm kind of like getting to the end. So for example, we looked at this so-called 2-poly channel, which is a member of this channel family of poly channels, where one of the poly operators occurs with some probability. And here in this, for this special channel model or noise model, only the X and Z error can happen with equal probability. Okay. This is a nice test bed, because for this channel, it's actually very hard to find superadditivity. So there's some work by people who have worked on this in the past, and they kind of like struggle to find this. And using our permutation invariant code ansatz, we were actually able to find pretty nice examples of superadditivity. We found that the maximum using this code family that we checked occurs around n equals 20 or 24, I think. And let me just mention two things. First of all, this is the so-called single letter threshold. So this is the best thing you can get when you only check one copy of the channel. The blue thing is what before our paper was the best threshold that they found. And so like the difference between these two is superadditivity. And then what we found is this threshold here. And so if you look at the numbers, it's a very small magnitude, but in our world, this is good. Yeah? So we were very happy when we saw this, because it kind of extends the threshold way beyond what we knew before. Yeah.
So is the key idea making at the, I guess, level of like a single qubit, they have a kind of high overlap, meaning that high overlap, but by having n copies, you make them distinguishable. Yet at the level of noises, it's like less distinguishable. So
yes,
noise cannot.
Exactly. So yeah, let me get to that. So the kind of states that we found have this threshold here, they actually look like repetition codes, but you take non-orthogonal input states. So it's not a 0 and a 1, but it's two states that have some overlap. And we actually found that a large overlap is good here, but when you take powers, obviously the fidelity decays, so they kind of become a little more distinguishable. But then the important point is, what do they do when the noise acts? And so somehow these non-orthogonal repetition codes, as we dub them, they somehow mitigate the noise better over when you have a orthogonal input states. But obviously, like as error correction codes, those are even less. They're even more useless than the repetition codes.
Lower bounds.
No, for the one-shot confirmation is known. It's okay. So that only they're only useful when you go to the n-copy case.
Okay.
Yeah.
But this is the lower bound, which will improve the point.
It is like all of these numbers here are lower bound to the corner capacity. So the true corner capacity here is some line above all of the things you see. So those are, every line is. Okay, I'm very short on time. Yeah, so here we try to visualize how these are non-orthogonal. We did some, let me just fast forward this. We did some analysis, like looking at the different IREPs and what contributes to the cream information. And here we see that the x-axis here is this overlap and the y-axis cream information. And you get a net positive for these non-orthogonal ones, but not for the orthogonal one, which is here at the right edge. I'm sorry, but I have to kind of rush through this a little bit. Yeah.
So I guess as n gets larger, probably you can make psi 1 and psi 2, the single qubit level getting higher and higher fidelity. Maybe in n goes to infinity limit, do you expect the fidelity to also go up and up? Or do you think there'll be a bound where if they are too close at the single qubit level, you cannot improve further?
I mean, we did go to much higher n, and we saw that this peaks at what I showed you. So, right, Sujit? Like we didn't expect any more gains, and we went all the way up to n equals 100. So we didn't attempt an actual limit computation here, but somehow they peak at a finite n, which is something that needs to be better understood as well. Okay, we checked other channels, for example, the one that you see in QKD. We did an analysis for somehow the simplex of polychannels and asked which channels do benefit from this overlap thing, like from the non-orthogonal repetition codes. And we produced some nice plots in the process. Yeah, unfortunately for the deparsing channel, which is somehow the end boss for all of these things, because even though it's the simplest of these channels, and has the most symmetry, it's actually hardest to improve this. And here exactly, so here what people have done is that instead of repetition code, you do a short code. So you do X followed by Z repetition code, and that does improve things here. The problem with short code type code stays is they don't have full rotation symmetry. So our ansatz doesn't capture them. You need to restrict the symmetry group, to a so-called Reed product of permutation groups, like one acting on each level of concatenation. And so this is something that we're working on these days. Yeah. So one plan that we have is to make the ansatz more general by restricting the symmetry group. Right? If I impose less symmetry, I get more states that satisfied. So this is kind of the dual thing here. So for the parsing channel, it has withstood our attempts here, but we do have some ideas for how to maybe improve things here. Yeah, and so let me maybe close with two open problems that have been open for a while now, and they're all involving this idea of trying to evaluate some entropic quantities on large systems. And then because you cannot do this efficiently, it's very hard to actually say something. One of these open problems is that entanglement actually helps in classical communication, in transmission of classical information, which is very counterintuitive if you think about it. But it's somehow true, and it was long believed to be false until Matt Hastings in 2008 proved that this actually does exist. So there are channels that when I don't just use product encodings, I can actually transmit more classical information. So somehow, even though I don't use the entanglement in the decoding process, they still boost the rates. And so he showed this by showing that this exists with non-zero probability. So he wrote down an ensemble of random quantum channels, among which, with non-zero probability, there will exist a channel that has this feature. But there's no known de-randomization of this. So we do not know how to write down an explicit channel together with an explicit code that actually does this. So we have no idea what types of channels benefit from entanglement in classical information transmission. And the examples we do know are random channels, so there's very little structure in them. And one goal in quantum channel theory is to understand this better by actually finding explicit channel models. And a very ambitious hope or goal of mine with this research program is to somehow use this symmetry reduction idea to maybe get a handle on this, but it's gonna be very hard. The other one, which is not easier, is that of the existence of NPT bound entanglement. So this is an open problem in entanglement theory. There's foundational work by the Leditzky family in the 90s that showed that this is entanglement distillation. So this means that you have some noise entanglement, copies of noise entanglement, and you try to distill pure entanglement by somehow converting them using LCC into a bunch of EPR pairs or something. And there are states that have this property that when you apply the transpose to part of the system, then they remain positive semi-definite. So those are called PPT states, positive partial transpose. And it's actually not that hard to show that these PPT states are undistillable, meaning whatever entanglement they might have, you cannot really distill. You cannot turn this into useful maximal entanglement. And they also gave constructions of these PPT states that are entangled. So this really exists and is now called bound entanglement. Yeah, because the entanglement cannot be retrieved. They're useless for distillation. And the open problem is the converse statement. Yeah, is every MPT state, so every state that has a negative partial transpose, distillable? Or are there also bound entangled states that have a negative partial transpose? And this is again something where you mathematically there are known reformulations of this, where you basically check certain properties of states in this like large n limit. And here it's related to measurements that you make on the state. But then you check some eigenvalue thing, yeah. You check whether these things are PPT or something. And again, another very ambitious goal is to maybe use this machinery of representation theory to get a handle on some of these candidates for MPT bound entanglement. Again, a very hard problem. You typically say don't let students work on these things, and I will make sure that we address maybe more low-hanging problems. But like very long term, I hope to make some progress on these problems as well. And by that, let me just finish and apologize for going over.
Maybe one question. Question for the problem. So the dimension of the URAPs actually conflict with the. So suppose I have a quantum channel that is not going my side. Can I place some trade-off on the number of these attributes? Yeah, give a reasonable approximation.
Yes.
Reasonable hyperbolic.
Like in all of our discussions, you always you fix your channel, so your dimensions of the they are the constant. Yeah, exactly.
But is that possible? Like, for example, I have a function of like I want to have like a compound on the coherent conformations. I say with some theoretical bound on the number of properties and I choose to have some reasonable bound. Can I basically trade off?
Wouldn't the trade-off mean that the channel dimensions somehow change?
It's just like kind of always like a very large function. That's kind of what we're doing. And I want to have some bound on the coherent information.
Oh, I see what you mean. These types of channels are not handled by this framework. Like the corner capacity would have to be defined differently, I think. Because it's this is not an IID model, right? Because somehow your local channel depends on how many you have. So this is some kind of memory, right? So you're leaving the IID model here. It's an interesting problem, but very little is known information theoretically about these types of channels once you go away from this.
Okay, so let's thank the speaker again.
I don't want to keep you long because you have to teach, right?
I do have to teach in 27 minutes, so I have
Okay.
like time for a question.
Yeah, I was wondering for the two poly error channel.
Yeah.
Do we know the upper bound correction?
I mean, there's we don't know anything that's better than the no cloning,
Right.
the anti-gradability.
Yeah, and that's for two poly error, that's what?
Yeah, you can compute that. I don't know it off the top of my head, but like it's like known analytically. You can just prove what that is. But
Yeah, I was just wondering how close are those results to the upper bound?
not very close, unfortunately. So it's one of those things where, like the plot that I showed you, the best threshold that we get now is actually there's this gap between that and that no cloning.
Yeah.
point where we don't know what's happening. So that's still open. Like all of these. I mean, there's been a lot of recent work on these upper bounds, and some of them actually might improve the no cloning bound.